Hello friends, welcome to the 20th class of this course. In the last class, we were solving some problems based on systems with constraints. There we used Lagrange's equations along with the concept of Lagrange's undetermined multiplier to solve those kind of problems. In this class also, at first we will solve one such problem, and then we will move on to our next topic, which is conservation theorems and symmetry properties. So let's solve another problem. Problem 5, I think. Okay, let's call it problem 1. Doesn't matter. So the problem statement is find out the tension which we will define by T of the string and the acceleration of the objects for in the following figure. And the figure is so we have inclined plane which have inclination at both sides, and the angles are alpha 1 and alpha 2. We have a pulley here, and the two objects, they are attached with each other like this. So mass of this object at left side, it is m1, and the object on right side is m2. So we need to find out the tension in the string and the acceleration of the objects. Now let us define first the coordinates. So coordinate of the object with mass m1, we will call it the first object. So object number 1, and this is object number 2. For object number 1, let's define the coordinate by x. So, and the distance is from this point. Okay, so we are defining all the distances from this point, from the topmost point. So, let's define it as x and define this distance as y. So we have two coordinates, but these two coordinates are not independent because the string, its length is fixed. So we have a constant equation that is x plus y equals to a constant, and that is the length of the string. So let's call it L. So constant equation is x plus y equals to L, which is a constant. Or we can write f equals to x plus y minus L equals to 0. Then we have del f del x equals to 1 and del f del y equals to 1. Now let's define the kinetic energy. Let's calculate the kinetic energy of these two masses and the potential energy of them. So first of all, the kinetic energies. Then kinetic energy for the first object will be half m1 x dot square, right? Half m1 x dot square. And so the total kinetic energy will be kinetic energy of the first object, which is half m1 x dot square, and kinetic energy of the second object, it will be half m2 y dot square plus half m2 y dot square. And the potential energy will be so if we consider this yellow line as our zero potential line, so in this line the potential energy is 0. In that case, so the potential energy we can the zero potential level we can define it as we wish. So we are taking it at this level. So in that case, this angle is alpha 1 and this height is x sine alpha 1, and for object 2 this is alpha 2 and this height will be x2 sine y sine alpha 2. So in that case, the potential energy here, the potential energy is 0. So in that case, for object M1, its potential energy will be minus M1g, and this length is x sine alpha 1. X sine alpha 1. X sine alpha 1. Because as we are going downward from this level, the potential energy will decrease. And it will decrease by mg x sine alpha 1. And for the second object, it will decrease by m2 g y sine alpha 2. In that case, our Lagrangian will be t minus v, which is half m1 x dot square plus half m2 y dot square plus m1 g x sine alpha 1 plus m2 g y sine alpha 2. So we have two coordinates. In that case, there will be two Lagrange's equations of motion. The first one will be ddt of del L del x dot minus del L del x equals to lambda del f del x, and ddt of del L del x dot, it is m1 x double dot, because del L del x dot is m1 x dot, right, from this expression of Lagrangian. So it is m1 x double dot minus del L del x. So del L del x is m1g sine alpha 1. Okay, only x dependence comes in this term. So it is m1g sine alpha 1 equals to lambda. Let's call it equation 1. Because lambda, because del f del x is 1. We already showed it. And the second equation will be ddt of del L del y dot minus its y dot minus del L del Y equals to lambda del F del Y. In that case, so del L del Y dot is M2 Y dot, and ddt of that, it will be M2 Y double dot minus M2G sine alpha 2 equals to lambda. Let's call it equation 2. Right? So this is the Y. So these are the two equations of motion. So from this expression, now if we use this equation of constraint, so let's call it equation 2 and let's call it equation 3, because we have this equation of constant equation, and we are calling it, let's say, equation 1. So from equation 1, we can write, x plus y equals to L, and if we derivative it with respect to time, if we take the derivative with respect to time, we will get x dot plus y dot equals to 0, and if we take the derivative with respect to time once more, it will be x double dot plus y double dot equals to 0, or we can write y double dot equals to minus of x double dot. And in this, so in that case, if we put this value of y double dot in equation 3 and we subtract equation 3 from equation 2, we will get, so equation 2 minus equation 3, and we will get m1 x double dot minus m2 y double dot minus m1g sine alpha 1 plus m2g sine alpha 2 equals to 0. This lambda and lambda cancels, and we have this equation, right? Y double dot equals to minus x double dot, so we will put it here. So in that case, it will be plus x double dot. It will be plus m2 x double dot, and in that case, we will have x double dot times m1 plus m2 equals to m1g sine alpha minus m2g sine alpha 2. This is alpha 1. And we have then x double dot equals to m1 sine alpha 1 minus m2 sine alpha 2 by m1 plus m2 times g. This is the acceleration of the first object. If you want to find the acceleration of the second object, just put the value of x double dot here. You will get the y double dot. So it will just be the minus of this. That means if this object goes downward, if m1 goes downward, m2 will go upward. That's the meaning of this negative sign. So let's call it equation 4. And this is the expression of acceleration for the first object. For the second object, you can put it here and easily get the value. Now let's find out the tension. So how do we find out the tension of the string? So this tension, it is basically a constant force. So it is a force due to this constant equation, because the length of this rope, it is fixed. As a result, this rope is giving us the tension. So it's a force of constraint. The tension is basically a force of constant. So in that case, the force of constant, what we will find out. So the force of constant, that is Qx, it will be, so it is Q constant x, it is lambda times del f del x, right? And we know that del f del x is 1. So in that case, Q constant is lambda. And we can find out the value of lambda very easily by putting the value of x1 double dot in equation 2. So in that case, lambda will be from equation 2, lambda will be m1 x double dot minus, so m1 x double dot minus m1 g sine alpha 1 minus m1 g sine alpha 1. And now if you put this value of x double dot here, then you will get, so you will get m1 square sine alpha minus m1 m2 sine alpha 2 m1 plus m2 minus m1 sine alpha 1, and the whole thing multiplied by g. Now if you do the calculation, you will get minus sine twice m1 m2 sine, this is alpha 1, so sorry, you will get not twice, you will get m1 m2 times sine alpha 1 plus sine alpha 2 by m1 plus m2 times g. So then the magnitude of constant force, it is m1 m2 by m1 plus m2 times g times sine alpha 1 plus sine alpha 2. So this is the value of this constant force. And the tension, value of tension will be same as this value of this constant force. So this will be our tension, because the tension is basically a constant force which arises because the length of the rope is fixed. This is our tension force or constant force. So we solved then a few examples for these systems with constants. Now we will move on to our next topic, which is the conservation theorem and symmetry properties. Conservation theorems and symmetry properties. Let's say, so assume that we have assume a system. So let's say we have a system with n degrees of freedom. So in that case, to specify the motion of the system, we need in position coordinate, let's call it q1, q2, dot 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 qn, and we will need n number of momentum or velocity coordinate, which is, we can call it p1, p2, comma dot 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 pn, sorry, it's pn, or we can write q1 dot q2 dot 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 qn dot. So to specify the motion of the system in phase space, we need n set of position coordinate and n number of velocity coordinate, right? So the phase space is basically a space spanned by the position coordinate and the velocity coordinates. So it means to solve the motion, we need n number of second order differential equations or 2n number of first order differential equations. So basically we have 2n number of coordinates. So n number of position coordinates and n number of momentum coordinates. So we need those values of, we need to solve for those components, you know, q1, q2, qn, and we need to find out the expression of q1 dot, q2 dot, qn dot. So in that case, we will need either n number of second order differential equations or 2n number of first order differential equations. In that case, so for each second order differential equation, we need two constants of integration, and we have n number of second order differential equation. So in that case, we will need 2n numbers of constants of integration, mainly initial conditions. So we need some initial conditions from where we need to start. Sure. But the problem is, so as the number of variable increases, it becomes, the problem becomes more and more complicated. So in that case, most of the problems, most of the problems in real world or close to real world problems are not completely integrable. So in that case, we will not find any precise expression for these coordinates, or we will not properly solve the problem actually. But still, we can extract a large number of, or large amount of information about the physics of the system without even solving the equations of motion. We can extract a large number of, we can know about a large number of different properties of the system. For example, let's assume, assume we have a system where the potential V, it depends on the coordinates only, not the velocities. So it depends on the positions only. Depends on the positions only. So in that case, then if we calculate, let's say del L del x dot, then it will be del T minus V del x dot, and it will be del T del x dot. And we know that T is half m x dot square plus y dot square plus z dot square, right? So in that case, del x dot of this kinetic energy, it will be m x dot, which is momentum along x direction. So if we take del L del x dot, we will get momentum along x direction. Now assume that potential has no explicit x dependence also. Potential has no explicit x dependence also. So in that case, Lagrangian will also not have any x dependence, any explicit x dependence. In that case, del L del x will be 0. Then from Lagrange's equation, we can write ddt of del L del x dot minus del L del x equal to 0. It implies ddt of px equals to 0, because del L del x dot, it is already 0, and del L del x is already 0 because Lagrangian doesn't have any x dependence, and del L del x dot, it is the momentum along x direction. So then we can write easily from here that it is conserved or constant. So what we got here is, if the Lagrangian doesn't have any x dependence, any explicit x dependence, in that case, the linear momentum along the x direction, that is conserved, right? This is the linear momentum along x direction. Linear momentum along x direction. So if the Lagrangian doesn't have any explicit x dependence, in that case, the linear momentum along x direction will be conserved. Now let's generalize this result. Before that, let me give some definitions. So the first is canonical momentum. Canonical or conjugate momentum defined by Pi. It is a generalized momentum associated with generalized coordinate. Qi. The generalized momentum associated with the generalized coordinate Qi. So in that case, Pi is defined like del L del Qi. So this is called the canonical momentum corresponding to the coordinate Qi. So Pi is the canonical momentum corresponding to Qi. Similarly, what we got here, like the canonical momentum corresponding to the coordinate x is Px, which we got by del L del x dot. So similarly, this Pi is del L del Qi dot. Sorry, there is a dot here. So this is how we define the canonical momentum. Examples. Let's say our kinetic energy is half m x dot square plus y dot square plus z dot square, and our potential energy is a function of x, y, and z. In that case, canonical momentum corresponding to x coordinate, it will be Px equal to del L del x dot, which will be m x dot. Similarly, canonical momentum corresponding to y coordinate will be Py equal to del y dot equals to m y dot, and Pz will be del L del z dot equals to m z dot. So these are the linear momentum correspond along the x direction, right? Mx dot, x component of linear momentum. But this canonical momentum, it is not always have the unit of linear momentum. It can be something else, or it will not always be linear momentum. So for example, so let's say this is example A. Let's say example B is, we are in spherical coordinate, let's say in spherical polar coordinate. So in that case, the kinetic energy is it is m r dot square. So we are in plane polar coordinate. So r dot square plus r square theta dot square, and potential, let's say potential is a function of r only, or let's say r theta only. So in that case, p theta, the canonical momentum corresponding to theta direction, corresponding to theta axis, it will be del L del theta dot, which is m r square theta dot. Now this is not linear momentum. It is basically the angular momentum. And the unit of this angular momentum, or the dimension of this angular momentum, it is different than that of this linear momentum. So let's take another example. So for many particle system in electromagnetic field, we got the Lagrangian as sum over I half mi ri dot square minus sum over I qi phi of xi. Here the phi is the scalar potential, and plus sum over I qi a of xi dot r dot I. This a is the vector potential. So for a single particle, moving along x direction, we will have L, which is half m x dot square minus q phi x plus q a x x dot. Ax is the x component of the vector potential. So in that case, the canonical momentum corresponding to the x coordinate, it will be px equal to del L del x dot, which will be m x dot plus q ax. And this is not same as the linear momentum. So by the term canonical momentum, it doesn't always mean that we will get the linear momentum. It can be linear momentum, it can be angular momentum, or it can be something else. Right? Here, this is not the linear momentum. This term, this is because of the momentum of the field. So when you will learn about the electromagnetic fields, you will learn that the fields, they also carry momentum. So this term is due to that. This is the momentum of the particle, and this is the momentum of the field. So it is a, and x is in the suffix. So it is x component of the vector potential. This is how we define the canonical momentum. Let's define another thing, which we call the cyclic coordinate. If the Lagrangian of a system does not contain a given coordinate, let's say Qj. So it can contain Qj dot though. So it can contain Qj dot, but the Lagrangian, it doesn't have any explicit Qj dependence. So Qj is not, it doesn't represent for all the coordinate. It is, let's say, for some coordinate. Qj is some particular coordinate, and which is not explicitly present in the Lagrangian. So in that case, then the coordinate Qj is called the cyclic or ignorable. So I will explain why it is ignorable coordinate. So now let's see why it is called cyclic or ignorable. Can you really ignore it? The answer is yes. So let's see how. So if the Lagrangian has not explicitly depend on this Qj, so in that case, we will have del L del Qj equals to 0. Then from Lagrange's equations of motion, we will get ddt of del L del Qj dot equals to 0. It implies ddt of Pj equals to 0, where Pj is the canonical momentum corresponding to the coordinate Qj, right? So in that case, we can write that Pj equals to conserved or constant. It means the canonical or conjugate momentum corresponding to a cyclic coordinate is conserved. This is the conservation theorem of canonical momentum. Conservation theorem of canonical momentum. Now, one thing we must note down is that if the constants are present, so if constraints are present in the system, in that case, the Lagrangian equation is ddt of del L del Qy dot minus del L del Qy equals to lambda, which is like so times sum over lambda alpha, sum over alpha equal to 1 to m, let's say, del F alpha del Qy. So here the lambda alphas, these are the Lagrange's undetermined multiplier, and this F is a constant equation. So if we have m number of constant equation, so in that case, the Lagrangian equation of motion will look like this. So in that case, we can also write this equation like ddt of pi, which is canonical momentum corresponding to the coordinate qi, equals to del L del qi plus sum over alpha equal to 1 to m if we have m number of equations of constant times lambda alpha into del f alpha del qi. Sum over alpha, lambda alpha, del f alpha, del qi. So now if we want this term, this pi, if we want this pi to be conserved, right, this canonical momentum to be conserved, or if we want this ddt of pi to be 0, in that case, this term should also be 0. Along with that, this term, it should also be 0. So that means if we want the canonical momentum to be conserved, that means ddt of pi equals to 0, then L and F alphas should not explicitly depend on qi. So not only the Lagrangian, but the constant equations also, they should be independent of these qi's. If we want the canonical momentum corresponding to this qi to be conserved, right? So that's the kind of modified conservation equation for systems with constraints. So what we learned is, if a generalized coordinate corresponding to a displacement is cyclic. This displacement can be anything. It can be angular displacement, it can be linear displacement, or anything. If it is cyclic, that means the coordinate is not explicitly present in the Lagrangian. It means that the translation of the system has no effect on the problem. So if we change that coordinate, so as it is not explicitly present in the Lagrangian, then if we change that coordinate, the motion of the system will not get affected by that. So in other words, if the system is invariant or symmetric, invariant or symmetric under some translation along a given coordinate, the corresponding generalized momentum or the canonical momentum will be conserved. So if the system is invariant under some translation along a given coordinate, that means that if we change the coordinate, in that case, so if we shift the coordinate, in that case, the system is invariant under that change, under that translation. So which basically means that in the Lagrangian, the coordinate is not present. So in that case, the corresponding momentum will be conserved. Right? So the thing that the system is invariant under some translation, we will call that, we will say that the system is symmetric under the translation. That means it is invariant. This means the symmetry property, is closely related to the conservation principle. So it means that the symmetry property, by looking at the symmetry property, we can say that the corresponding momentum is conserved or not. So if the coordinate is symmetric, so if the translation corresponding to the coordinate is symmetric, then we can say that the corresponding canonical momentum is conserved. So the symmetry property is closely related to the conservation principle. So let's take an example and understand it. It's a very simple example. Like if a system is spherically symmetric, that means if you change the theta or phi, there is no change in the system. Or let's say there is no change in the Lagrangian. So in that case, we can immediately say that the angular momentum is conserved. So we don't need to solve the problem. We don't need the explicit solution of the problem. From the spherically symmetric property, we can easily conclude that the angular momentum is conserved for the system. This is how the symmetry property is so important. So in that case, so if the translation of a coordinate, under the translation of a coordinate, the system is invariant. So in that case, the momentum, the corresponding momentum is conserved. And as a result, we can ignore that coordinate in our Lagrange's equations of motion. So that's the meaning of this cyclic or ignorable coordinate. So it says that if the Lagrangian does not contain a coordinate explicitly, in that case, the corresponding momentum is conserved. It is constant of motion. So we don't need to bother about that. We can ignore that coordinate in our Lagrangian. So we can ignore the we can ignore the coordinate as well as its corresponding momentum, its corresponding velocity, qj dot. So if we have a cyclic coordinate, we can ignore that. So that's the meaning of this ignorable coordinate, right? So that's all for today. In the next class, we will talk about conservation of energy, and we will solve some more problems. Thank you.